All right, let's get started. So it is our great pleasure today to welcome Yiping Lu to the SNAPP seminar series. Yiping is a new assistant professor in IEMS at Northwestern University. Before that, he was a current instructor at NYU. And prior to that, he got his PhD at ICME at Stanford. Yiping has been recognized with a number of Rising Star Awards, including from the Rising Star in Data Science from the University of Chicago and the Conference on Parsimony and Learning. And we're very excited for Yiping to present today to us on using simulation to calibrated machine learning. Yiping, the floor is yours. We'll stop every once in a while for questions if they come up in the chat.
Mhm.
And please go ahead. Thank you very much for coming today.
Yeah, thanks for the invitation. Today, I would like to share you some my new thoughts on using simulation to calibrate machine learning. So to start with, everything, I just want to introduce the motivation of this line of work. So why we do research, it is because we want to do some useful prediction without doing actual experiments. So in the past, what we do is called scientific computing or stochastic simulation in our community. Where we do is, okay, we have a problem in hand, then we try to write down some model, maybe some queuing model, some operation management model. For physics, we will write down some differential equation model or anything like this. Then we tell our computer, okay, here is my model. Can you numerically solve that? So we numerically solve the models that we write down, and that's our prediction. So we need mathematicians to write down the model and need numerical analytics to use numerical analysis to analyze the algorithm, whether it converges, whether it's good, and then we can make our prediction. But things looks changing these 5 years. So for these 5 years, if you want to make useful predictions, then the things you need to do is, okay, we first collect many data. Once we have data, then we just need to hire even undergrads to just download code from the PyTorch and feed it into a neural network. And it sounds like the neural network can magically learn everything without even knows what is the problem we are working on. So it sounds like here is a debate whether we should go to the left-hand side or the right-hand side. And for machine learning scientists, we don't have any guarantees. Although these years, if you go to machine learning conferences, you can always see theorems like this. If you randomly collect how many data, then you can achieve a good accuracy with your AI. And even papers like this can prove that, okay, machine learning algorithms are optimal in many sense. But do we actually trust that our machine learning algorithm can give me trustworthy predictions? The answer is definitely not. These theorems appear at these machine learning conferences. They need a very strong assumptions like a global optimization, the structure of the target function, and even some paper assume that the ReLU function is a smooth function, or you need to assume your density observed have a lower bound. Or all these kind of assumptions is not satisfied in real world applications, and these optimality results actually don't provide us any trustness on the machine learning predictions. So for today, I will show you a marriage. I will use the machine learning technique with the simulation technique together. I will combine them together to give you some nice things. So we know that machine learning can do good in average case. You just have average data, the same distribution as you sampled. They can give good predictions. At the other side, because our mathematical model is written down very rigorously, mathematical funded, so it can guarantee the prediction in the worst case. So for today, I want to show you that there is a line of thoughts I have made to make all these things happen in the same these two things can happen together. And for today, I can also show you that even your machine learning algorithm is biased, I can still do unbiased prediction uh, using the structural model. But if your machine learning algorithm is optimal, all the prediction I gave today is also optimal. So this is today's marriage I will introduce. So if your neural network gives you like a good prediction, no, then let's just follow the neural network's prediction, right? We don't need to do any like further simulations to see whether my neural net or to see what is actually the worst case guarantees. But if your neural network is bad, then I want my algorithms switch to the stochastic simulation algorithms, because now my neural network is bad, it doesn't tell me anything. The only thing it tells me is actually the simulation algorithm. And so this is like today's algorithm. We will combine the stochastic simulation algorithms with the machine learning algorithm. The way is to do a calibration, so which I will show you later. So in this way, you can see I can combine all these things together. And if your neural network is good, my algorithms will provide you the neural network solution without any further computational cost. But if my neural network solution is bad, then all my algorithms will go back to the traditional simulation algorithm, which can give you the guarantee in the worst case. So this looks like the philosophy I will introduce today, but it's vague. Let me introduce you like the thing I will show you in a mathematical framework. So today I want to show you even your machine learning is a biased predictor. I can still use an algorithm, use a simulation algorithm to unbias it to provide you unbiased prediction. So let me show you what is like the framework here. So for machine learning, which is something I just want to abstract it as this. So for machine learning is I want to estimate some parameter, let's say theta. It is that how we can estimate the theta is like we have a distribution of data, which is parameterized by the parameter theta is the p theta. So I simultaneously sample data from this distribution, like x1 to xn is the RID data that I sampled from the distribution p theta. And I want to use a machine learning algorithm like max likelihood or any other algorithm you want to get an initial guess of my theta. So let's say I can estimate the theta to theta hat. This is my machine learning algorithm. But for today, I can't debias this kind of algorithm using simulation, because we know in many of the cases, machine learning algorithm is the optimal algorithm for the setting. So for today, I will consider one step further. So once we estimate our machine learning parameter theta, like the environment, once we know the environment, we always want to do some downstream applications. We do not just like provide the theta to the public or to the applications. The thing we will do is maybe we need to do some like decision making. Maybe we just need to report some statistics. We do not need to report all the environment to the decision maker or to the public. We just need to do some downstream applications to provide it to the users. So now we consider one more downstream applications. When we consider the downstream applications can make the applications easier, the reason is my theta is all the environment like we are working with. Maybe the theta is a function which is infinite dimensional. But for the downstream applications, we just need to provide some summary statistics. So the downstream application phi is actually a functional that maps from an infinite dimensional function to a real number. So for a real number, it may be easier to predict than the whole functions. So today I will show you there is actually chances to improve once you consider these downstream applications. Then you can do a biased prediction of phi. Even your estimation of the theta hat is biased. So how can I do this? So if I want to do this, we know that if I already get some prediction called theta hat, the thing we will do is directly plug that into downstream applications, which is phi theta hat, which is biased if your theta hat is biased. But if I want to debias my prediction phi theta hat, what's the thing I need to do? To debias a biased prediction, the only thing I need to do is to estimate what is the bias that I have made. So for today's talk, I will show you that in many of the downstream applications, this quantity, which is the bias of my downstream applications, is actually have a chance to be calculated. So today's idea is, can we use stochastic simulation algorithm to calculate out these bias of the downstream applications so that we can use the stochastic simulation algorithms to calibrate the machine learning output? So let me show you like some examples here. Oh, sorry. So before the examples, these are the two main questions I would like to answer today. The first thing is how I can estimate the bias, how I can construct unbiased simulation algorithms for the bias. And the second thing is why we still need the machine learning algorithm, right? So we can directly plug, if you can simulate this, I can directly plug in my theta hat as like a simple 0. So what the thing you are working on is just a simulated phi theta. So why the theta hat here, like the better machine learning algorithms will make the problem easier. So here are the two answers. Yes, firstly, I will use like the structure of the phi so that I can write down Monte Carlo algorithm to estimate my bias here. And why the machine learning algorithm will help you is actually I can show you a better machine learning algorithm actually can lead to a stochastic algorithm, a simulation algorithm with lower variance. So my machine learning predictor here is no longer behaves as something prediction, but I will use it as like a variance reduction. So this looks like still like very vague. Let me give you like my first example here. So the first example is my downstream application is just to estimate the moment of a function. Okay, so now I have a function I want to learn, so I can get the data that is from like my function f here. But the thing I want to estimate is just like the moments of my function here, which maybe means the temperature, which means maybe the overall mean or the higher order moments that we just need to know the summary statistics. So in this setting, how we do this kind of thing. So let me first consider the mean case. Let's just consider the simplest mean example. We still doesn't do like for the Q's power. So let's first consider the mean example. So what does the machine learning mean here? So now I want to estimate the mean of a function. One thing we can do is, okay, let's first learn a function f hat, which may be a neural network, maybe kernel smoothing, or maybe even simple as polynomial regression. So let's use all the algorithm that you like to get an estimation of your function f. So which is my function f hat here. So then we can get my f hat here is the grade dot function here. And then now we can approximate the mean of my function using like the grade dots here. Then you can calculate the mean of the f hat to replace the mean of the f. So this is nothing new in your textbook. This is just called the Simpson's rule, which is the most traditional way to calculate the integral. So this is called Simpson's rule. But let me show you that how we can use a stochastic simulation algorithms to make the estimation better. So now we need to estimate what is the error that made by this directly plug-in estimation. So if we write that down, the error we made is actually the expectation of f minus f hat, which is the error of your machine learning estimators. So how we can do this? Let's just do a Monte Carlo algorithms. So we first using first half of my data to learn my f hat, and then I use my second half of my data as like validation data set. So all the purple data point here is the validation data set. On the validation data set, you can actually look at what is f minus f hat, right? Because at this time, f hat is something I learned. I just need to plug in my data, so I know what is my f hat. I also knows my function f, which is from my data set. So you can easily get like this, you can easily calculate out what is the error here, which is f minus f hat here easily. And then a simple Monte Carlo algorithms can help you to compute out what is the mean here. Okay, so this is like how the simplest example shows you there is actually chances for you to estimate out like what is the error made here. So why this is better than directly estimated phi? So what does the directly estimate the mean of my function f without a machine learning algorithm is actually the Monte Carlo algorithms. So for the Monte Carlo algorithm, we directly sample like the function values and compute out the mean of the function values, and this is the estimated mean. So why our method here is better than the method I show you, like the naive Monte Carlo method. So for the variance here, the variance is actually the variance of my function f. But for here, the variance is just the variance of the small residues here. So these residues are small because maybe my machine learning algorithm is good. And in the perfect sense, my machine learning algorithm is just like the direct estimate, the true ground truth function f. So all the residues here are zero. I can get a zero variance simulation algorithm. But for here, your simulation variance is always a constant because it is actually the variance of my function f here. So we do a variance reduction, but maybe some of the audience is confused. What's the thing? What's the difference that I'm talking here? Different from something called regression adjust control variance, because I use a machine learning algorithm as a control variant to reduce the variance in the literature, which is just known as like regression adjust control variance. So if you are working on like reinforcement learning, you may also confuse this looks like some very similar to doubly robust estimators, because here I have two estimators. One is the machine learning, like the Monte Carlo algorithms, another is the machine learning algorithms. The thing I'm telling you is that if one of them is good, then my algorithm is good. So actually the philosophy is actually the same. So the philosophy I'm doing today is both regression adjust control variance and another is doubly robust estimator. I can achieve the both goals of that. But for today, I will show you something interesting. The first thing in the first half part of the talk is a theoretical analysis to show you what is like the harness of these problems. So we investigate like this optimality result of this kind of framework. And this is the first part of the talk. And in the second part of the talk, I will show you this kind of things for doubly robust estimator and both regression adjust control variant. Most of the applications is like linear functionals phi, like calculate out the mean. But for today, I will show you, you can actually extend these kind of ideas to nonlinear functionals using some ideas of iteration methods. So these are the two things, the two main contributions I will show you today. Let me first go through the theoretical part. So for the theoretical part, why our algorithm is better. So if you work on like doubly robust estimator, this is something it sounds very familiar. So the first estimator I'm saying that is if I want to compute out like the expectation of my function f over the distribution p. The first thing I told you is I can estimate like a function f hat, which is similar to my function f. So I can compute out this thing. So the error here I made is actually just f minus f hat. So I write that down. So it's like I want to estimate x times y. I gives you some estimation is some y hat, and the error made down is y minus y hat. And the second algorithm I'm saying is the Monte Carlo algorithm. Is that okay? I know you are doing expectation over p of my f. So maybe I can replace your p to some easy p like the empirical distribution p hat. So I can still make the prediction. So now I write down that. So it is like x times y is equal to x hat times y. So the error we make here is p minus p hat, which is x minus x hat here. So like I also have some friends in the applied math community who is like to do this like numerical integration. So if you have some like you may heard some debate from that community. So it's that everybody is doing a debate. The first way is better, approximating f is better, or estimating the p is better. So they will always have a debate saying that if you are using high dimensional regime, estimating p is better. If you are in low dimensional regime, estimating f is better. But today, the answer is actually not. Both of them is not the optimal algorithm. The optimal algorithm is you can actually combine these two estimators together. You can write down something like this. Then your error will become y minus y hat times x minus x hat. So this is like the idea of debiasing. So you can first estimate out what is your first algorithm, and then you compute out like the residue to use the second algorithm. Then you can do an error that which is just the residues, let's say, times together. So let's say the first algorithm, which is like quadrature rules or machine learning based predictors, then they have like computational, like convergence rate is to the alpha's power. And then for the second estimators, then the convergence rate is into the beta's power, which is the Monte Carlo algorithms. Then the algorithm I can achieve is actually times these two things together is alpha plus beta's power. And this is actually how doubly robust estimators works, because for doubly robust estimator, what they said is if one of them is actually zero, then your estimator is still zero. For today, I will answer this question in a very general framework to show you like this is actually an optimal framework. We can build both min-max lower bound and upper bound to show you that this algorithm is optimal. And the regime we are actually working is non-parametric setting. So for the non-parametric setting, the hardest thing is actually to select a norm to evaluate y minus y hat and x minus x hat. Because we times these two things together, so the thing maybe trivial is we need to select these two norms to be some kind of duality norms. So this norm, the selection of the norm will becomes like the most important questions to build up the optimality result, which I will show you later. And this may give you some insight how you train a machine learning estimator that is best for the simulation algorithm. Because the thing you need to do is to select out what is the norm that affects your simulation algorithm. Okay, so the question we investigated in our paper is this simple question. Yes, we just need to compute out like the moments of the function once you know what is the function value. So the class of function we consider is actually some Sobolev function class, which my function have S gradient, and the S gradient have P's norm here. So this thing is bounded. So we consider like my function is just a smooth function which lies in the Sobolev class. So why we select this P norm here, I will introduce it later, because if I don't introduce the P norm here, the function must be regular, means that my function will be bounded, which is actually an easy regime. You can follow all the proof here. But if once you can introduce the P norm here, then you can imagine my function may have some spike. So we want to introduce a function with spike to model some like real events, which is like extreme but real to happen using like these kind of Sobolev functions. So we want to answer the question. So if my function f lies in this space, the algorithm I written down before to estimate the Q's norm, whether this is an optimal algorithm. The answer is yes, but in some regime. So let me first show you the lower bound. So the lower bound is actually the example I show you why I want to introduce the p norm, piece order p norm for the Sobolev norm. The answer why we consider this, because we want to consider two kinds of hard examples. The first kind of hard example is like my function is a smooth functions, so my functions may be a composition of some random flips. Some of the function is plus, some of the events is negative. So I want my functions to predict some of like these random flips. This is one kind of functions, which is like small flips. But there is also another kind of function can be included in my framework, is that my function is just a single spike. So the magnitude of the spike will be bounded by the smoothness of the functions. So this is like two kind of functions. Let me first show you like the first kind of functions. So for the first kind of functions, the magnitude of these random flips will be bounded like by your your smoothness. So if you have like n data, then the every events you will see here is probability at 1 over n. And the magnitude of these random flips will become the smoothness over the dimension, which is like the normal result you will see in the non-parametric regression. You will always have like small bumps at the rate of smoothness over dimension. But there is one more thing is here. You will gain another half here. So the actually rate here, the half is from the Monte Carlo algorithms, and this as smoothness over dimension is from the smoothness over the functions, which can be captured by the machine learning algorithms. So this regime looks like very, very similar as what I have showed you here. So which is like beta is the half, which is the Monte Carlo algorithm. Smoothness over dimension is like the algorithm of my machine learning rate. So this is what happens in this regime, which is like actually something easy. But for this regime, it looks like different stories. So because now my functions may have a spike, which models like these rare events may be extreme. So now you can consider the real events we can capture with n data is the real event what happens at the probability 1 over n, right? So if you have a real event happens at the probability 1 over n, the magnitude you can compute out is actually something will depend also with my parameter p. So this is the reason why we introduced the parameter p, so that we can model this kind of spike function here. So for these kind of spike functions, then you can see this is actually the magnitude of the spike you will make. And the Q here is actually the moments here. So because your function will have a spike, then this Q will make this spike larger. So you need to times your Q with how much is your spike here. And here 1 over n is because this is what will happen because this real event will happens at probability 1 over n, so you will get a rate of -1 here. So this is like two hard case. One is spike, one is random flip. Then we can build like this very easy lower bound here is if you have spikes, so if your spike is dominant, then you will have a convergence rate. So the x-axis here is the smoothness of the function. So if your function is not smooth, then the spike will dominate, right? You will have some very extreme spikes. So when your function is not smooth, then the hardness is dominated by these spike functions. So if your function is very, very smooth, then the hardness will be dominated actually by this kind of random flip, because the spikes here will become very, very small. So you will have like this phase transition happens between like spike function and random flips. Okay, so now this is like kind of things you will imagine will also happens for the upper bound for building algorithms, right? You may also have some algorithm to capture the spikes and have some algorithms to capture the random flips. But actually now, the surprising thing is the optimal algorithms we covered have a different transition point. So this is like kind of like the algorithms we discovered to be optimal. So there is actually, yes, still two regimes. The function is non-smooth and the function is smooth. And for the function is smooth, the optimal algorithm is like a regression adjusted control variable. You can call that. You can also call it like a doubly robust estimators, but you can also call that my name here is like using simulation algorithm to calibrate machine learning here. So this is like kind of like the algorithm to make the optimal prediction, which is a blue regime. And for the when the function is like very, very smooth, very non-smooth, that all these things happens is like these spike functions is the hard examples. The optimal algorithm is actually some truncated version of Monte Carlo algorithms. Because in this case, my distribution becomes some kind of heavy tails. So you need to truncate your algorithms to get like a good result. So the transition point here is not actually the transition point we see in our lower bound. The transition point happens here is actually whether your real events is a finite variance one. So this transition point is exactly the point that the yellow regime here is exactly the regime that your spike functions have like have infinite variance here. So if you have infinite variance, then the truncation will becomes like essential, because you want to simulate the mean of a random variable which is actually have unbounded variance. The thing you need to do is, if I have more simulations, I truncate it like with higher values. So it is like actually a bias and a variance trade-off. If you truncate it at higher values, then I will have higher variance. If I truncate it at a lower value, then I will have more bias here. So in this regime, is actually to do a bias and a variance trade-off. So
Yiping, can I ask a quick question?
yes.
So, do you assume that you know which regime you're in, or do your algorithms automatically figure it out?
This is a quite good question. So in this work, we are still not adaptive. So we try to write down some adaptive thing, but most of the adaptive thing is actually just that I'm adapted to the smoothness when the function is lies in the blue regime. This is most of the adaptive work too. I still doesn't see an algorithm that can adapt to both regimes I have written down. Yeah, that's a
I see.
interesting thing. Yeah. Yeah,
Thank
yeah.
you.
My algorithm here is still not adapted. We need to know which regimes you are licensing. Yeah, yeah. So now for the yellow regime, the most important thing is the bias and the variance trade-off. You need to know how much you need to truncate your Monte Carlo algorithms. Then we want to know why there is actually a transition point in the blue regime, right? So if you will consider that, okay, if I want to analyze the algorithm here, I will write down the proof, and the proof will give me like a algorithm don't have a transition point. But why the proof of like the blue regime, the algorithm is the same, but it looks like they have different behaviors to the spike and the smoothness. Why there is a transition point here? So let me first introduce like the easiest regime. So the easiest regime is here is actually my function is very, very, very smooth. So that my function is actually bounded. So you can see the story here. So the smoothness over the dimension is hardness that you estimate your function value. And the half is actually the Monte Carlo rate. So you just times these two things together using the framework that I showed you before. You just times these two rates together, you can get the optimal rate by function estimation error times the Monte Carlo rate. This is like actually the easiest point, which is actually a very, I forgot to cite the paper, but this is actually a recent paper which also do the same thing. So now the interesting question is when you have a real event. So you have an event that may go to infinity, you don't know how I can bound that to real events. So, but the real event is finite variance. This is actually a very, very interesting regime that we done in our paper. We show that why the reason here for the upper bound, we still have a transition point. Okay, so now let's consider how we need to analyze the error propagation. What does error propagation here means? It means I have a machine learning algorithms. I use the machine learning algorithms to do the second stage like simulation algorithm. I want to know what is the error made in the machine learning algorithm will leads to the will leads to the like the variance of the simulation algorithm, how these things propagate from the error of machine learning to the variance of simulations. So the hardness of the algorithm is actually the variance happens at this debiasing step, which is f the q to the q's power minus to the machine learning algorithm to the q's power. So the thing we do here is actually a very, very simple thing to see what is actually the leading power term here. So the leading power term here, the first thing is you can do a Taylor expansion. Then this is like the error you made of your machine learning algorithms. This is the gradient here. So this is maybe the first leading term. But maybe the second leading term, because here I'm is to the q's power, maybe the second leading term here is how my error propagates here is actually the error to the q's power. So this is the reason why we can see a transition point here. So here is a transition point is because the leading point here is not simply like just one term. There is actually two terms may happen as a leading term. And you will see for our proof, so for our proof, these two regimes is just, these two regimes is just two leading terms that dominates. So how we deal with like this still complicated form. So this is like our main proof technique, but I will not introduce this today. But basically the main ideas that makes everything work is we need to embed these two things into the do function space because the things I'm estimating is actually these two things times together, right? So if we want to bound these two things times together, we need to know their norm in a do norm. So the good thing is we do a very careful calculation of the norm selected, then we can find out that there is actually exists a norm. We can find out that to make every proof becomes optimal. And here is actually the norm we selected. So it looks very tedious. So I don't want to do the calculation here. So this is actually our main contribution here is to select out what is the best norm for the computation. for in the control variable. So you need to embed that into different norms to get the optimal result. And in these two regimes, it is just like two different like leading terms dominate. So that will lead you into like different regimes. So this is like the basic things that we have discovered. And the second thing that inspires us is actually this embedded norm. This thing actually tells us that if you want to train a machine learning algorithm for a simulation algorithm, the evaluation for the machine learning algorithm is no longer the L2 norm we do like for most of the machine learning algorithms. The norm we consider here should adapt to the simulation tasks that we are operating, right? So we need to, so this like leads to new challenge for the machine learning algorithm is that I have a new simulation algorithms. Or we have a simulation algorithms. Then we need to write down the criteria to make this simulation algorithm have lower variance. This is the new criteria that we need to let our machine learning algorithms to satisfy. And this is the first intuition that brought by our work. The second intuition is here is actually leads to a real event. We make a function class that may behave in figure B, which may have like a spike, which is some real and extreme events. So if this kind of like this real and extreme events is actually have infinite variance, then the machine learning algorithm is actually can't help you too much. So the machine learning algorithm may just help you to up to a constant, but it will not improve your convergence rate. The convergence rate is actually dominated by, because you are infinite variance, you need to do a bias and variance trade-off. So everything is actually stuck. The bottleneck is the bias and variance trade-off. The machine learning algorithm may just help you in a constant, but it will not help you in the convergence rate. And if your function is just like this, like smoothing, very smooth function show you in figure A, then now the machine learning algorithm can actually help you. Like you can time these two rates together to get better result. So this is actually another like intuition, maybe not right, but this is something I'm hypothesizing. It's like the things like doubly robust estimator, regression adjust control variate may just help you in like these regular cases, shows you in figure A. Once you go to like this rare event and extreme events in figure B, the things you need to do is actually the probability analysis, but no longer adapt up doubly robust or regression adjusted control variate to let machine learning algorithm helps you. So this is the intuitions that brought from our theoretical analysis. And for another half an hour or 20 minutes, I want to show you this is actually a family of algorithms that you can do to using like these the biasing ideas. You do not need them to be doubly robust. Doubly robust is too strict to satisfy. They can just satisfy for linear examples. And for regression adjust control variate, you just consider simulating a mean. This is also like constraint. So you can actually using this idea, using simulation algorithm to calibrate the machine learning output, you can actually get a family of algorithms for many of the applications. So what is actually like this idea of using simulation algorithm to calibrate the machine learning algorithm actually doing? So first of all, we first using a machine learning algorithm to fit the rough information of the function or the rough information of the environment that I'm working on. And the second step, we use a validation data set. We need to know how the machine learning algorithms have made wrong on the validation data set. So we know how much maybe these machine learning algorithms, we get a data set to describe how like this kind of machine learning algorithm have made wrong. And the third step is we can collect all these errors together to get an estimation of like this phi theta minus phi theta hat, which I will show you examples later. So before we go to like my algorithm written down, there are actually some other interesting examples in the literature, which we know is the optimal algorithms can be written down in this framework. Let me show you the second examples. So the second example is looks like this. So is I want to estimate the trace of a matrix AA without knowing the matrix. Because knowing a matrix, like the matrix is maybe the agency matrix of a graph, or the A matrix is a very large matrix, so it's very hard to like restore all my matrix A in my computers. So now what I can do is I can get a data set. The data set is actually the vector and the matrix vector multiplication. Matrix vector multiplication may be fast for graph examples, right? So now the things I can get information from of my matrix A is actually just matrix and vector multiplication. So I get a data set X. This is like all the information I can get from my matrix A. And what is the optimal algorithm to compute out the matrix, like the trace of my A? So maybe you can consider Monte Carlo algorithm to compute out the trace of A, because the trace of a matrix can be written down as a expectation over random vectors of AX. X transpose AX, that is then called Hutchinson's estimator, which is a Monte Carlo type of estimators, but actually not. The optimal algorithm that is discovered, this algorithm is proposed in a paper from Berkeley, Mass, Lin's paper in numeric in this, and later David Woodruff groups at CMU proves that this is actually the optimal algorithm for computing out the trace. The idea is actually simple. First of all, we can first do like a estimation of my A, low rank estimation of my A using the data set here. So this is actually known as randomized SVD in the literature, which is said, okay, I do some randomized X and I can get the estimation of my A, but only in a low rank subspace. So they do this estimation in the low rank subspace using randomized SVD, which is gets my matrix A hat. And then they estimate the difference here, like the trace of A minus A hat using the Hutchinson's estimators. So this is actually the kind of the same kind of idea that I have introduced. You first use a machine learning algorithm, which is a randomized SVD algorithm, to get the estimation of your environment, which is the matrix A here. And then you use a Monte Carlo algorithm to estimate what is actually the error of your first stage estimations. So this is like many of the other algorithms can also be written down in these kind of ideas. Another example I don't include in slide, but if you work on conformal prediction can also be seen type of Monte Carlo algorithms. So there is actually a NeurIPS 19 paper by Emmanuel Candice called quantile conformal prediction. So for that paper, they first use a machine learning algorithm to predict what is the quantile of the distribution, which is forms like the confidence interval, but then they use the conformal prediction to do the debiasing. So many of the algorithms you can see in the literature can be written down in this framework. So now I will show you, but for most of the work, the downstream application functional here phi is actually a linear functional. So now the nature question you may ask is what will happen if phi is nonlinear, right? So for today's talk, I will show you there are many cases that you can use iterative solvers to replace like this nonlinear functional phi. So the first example I will show you is to do high dimensional control to solve high dimensional HAB equations. Okay, so what does like machine learning algorithms or like function estimation algorithm mean for like HAB equation solving? So you can use like neural networks to approximate a PDE solution, which is called physics informed neural network. But if you don't know about that, but you can also consider you just have some finite element or any other numerical schemes you have already got for the PDE solution. So now what you can get is actually to solve like the PDE is like Laplace U equals to F, which is the value, which is the Bellman equation for the Brownian motion. So you can consider the things you can get is actually F is a reward function. So you get a data set, which is actually like the data set of the reward function, but the things you want to recover is actually the value function U here. So you can use like finite element method to approximate this equation to get a solution. You can use neural network method, which is called physics informed neural network family. You can get like a neural network solution to that. And then the question is, if I have these downstream applications, can we debias that? So this kind of downstream application we written down here, maybe it's the mean of the value function, maybe the variance of the value function, or maybe simplest thing is actually let's just consider I want to get the value, I just want to get the value function at a given space. Okay, I just want to know, you give a space, I want to know the value function. Does there actually a way to do the debiasing? The answer is simply yes. The idea here is, okay, I know my true value function satisfies the equation Laplace u equals to f. But now I get another estimation from like Gallatin method, finite element method, or kernel method, or neural network method. It is called u hat. So now we can write down what is actually the function, the value function u hat maps to another reward function. I call it f hat. So you can just calculate out the Laplace of your estimate solution u hat to get the f hat. So this step can be computed out because your u hat is a kernel method or neural network method or finite element method. You can always to get out what is the gradient, right? So you can compute out what is your f hat. And now the arrow I want to do is actually just minus these two equations because the Laplace here is linear. So you will see the Laplace of u minus u hat is actually another Bellman equation here. So we know that, okay, my u minus u hat is actually the solution of this Bellman equation with reward function f minus f hat. So you can do this minus here. And then because we know this is actually the value function of a Brownian motion, so to get like Monte Carlo estimation of the thing you need to do is just to simulate out a Brownian motion and collect all the error over the Brownian motion. And in expectation, this is actually your u minus u hat. So why this is easier than just work like a Brownian motion? The reason is f minus f hat is actually the residue of the reward function, can be a very small reward. So the variance of the reward over like this path can be small. But if you want to just collect the reward function over the path, which will becomes higher variance. So now this is the second example to show you to solve high dimensional differential equations. You can actually use your learned PDE solution as a control variate, but not like directly use it as a prediction. So this is like a linear PDE. You may say, okay, I'm cheating because I'm using a linear PDE here, so everything can be easy. But actually, we can do nonlinear PDEs. So the only thing we need to do is we can do nonlinear HAB equations. So, but the only thing we need to do is because we need to keep the Brownian motion simulation structure here. So we still need to have a Laplace here. So our idea here is, okay, also all the other things are nonlinear. But we only need to keep the linear structure of the Brownian motion simulation. So to do that, so first of all, these semi-linear equations can be simulated using Brownian motion, so which is called multi-level Picard iteration. I don't have time to go through that today, but you just believe me that there is a 2016 paper showed you that even you are nonlinear equations, unless you have like Laplace here, you can use Picard iteration plus Brownian motion simulation to simulate out these kind of nonlinear HAB equations in high dimensions. And now the things I want to show you today here is actually this step can be done even for nonlinear equations. So this is how we work that out. So we, as the same thing here, we first have like a neural network or kernel or finite element approximation of this solution here. Then we just write down the new equation for the u hat here. So, but the only thing here, you will get a residue that the error of a neural network that made. Then we minus these two equations here together. So the good thing is, okay, the first thing like is linear, the Laplace structure is also linear. So all the things here can still be kept in a linear structure. So our idea here is for all the nonlinear terms, okay, it can be written down in a quite complicated nonlinear term. But after you organize everything out, you can see it is just a new nonlinear function over u minus u hat. So after you minus these two equations, the Brownian motion simulation structure is linear, you keep that, and the only thing is the nonlinear function is changing, but everything you can still write them down out as a semi-linear equations. So you can still use like the Picard iteration method, the Picard multi-level Picard iteration method to simulate out these kind of equations. So this is like our numerical. So this is our numerical result. So this is like you use neural network method to solve the PDE. This is like the error you made, and this is the error made for the multi-level Picard iterations. But you combine these two methods together, you can get a method that get lower level accuracy. But the drawback is you can just do this over like a fixed space-time point. It is like, okay, is it like policy evaluation, but it's not like learning all the policy here. You can optimize the optimal space point. So you can just do that over like a single space-time point. So the same story will also happens here. So if your neural network converges over like smoothness over dimension, and your multi-level Picard iteration is like some Monte Carlo rate. So why is there not Monte Carlo rate? Because this is actually is actually a branching tree simulation. So it is a branching tree simulation. So it will have like 1/4, which is the standard convergence rate here. So you can see the thing I can do here is I can combine the branching tree simulation with the smoothness over dimension together to get a convergence rate for the algorithm here. And a similar thing will also happen for higher dimension. And the most exciting thing we are still like working on more experiment is that if you put it in more and more higher and higher dimension, our variance, our like variance stabilization effect will becomes more and more. So we still want to understand this, but in experiment we just show things like this. So you can combine these two kind of algorithms to get a new algorithm here. And something fancy I want to connect it with is actually, I want to connect that with like ChatGPT. So if you know the new ChatGPT 01, the strawberry, so what's the idea of their algorithm is, okay, we can first train a large language model, and then we just get out what is the answer from the ChatGPT. This is like the previous ChatGPT. But the new ChatGPT 01, what they do is at inference time, they will still do a tree search algorithm to search for the best answer. So they still do like algorithms over the inference time, but not just doing training and testing. So they have two types of algorithms. One is happens at training, and one is happens at inference time. So this is actually the same kind of idea as we made in our kind of algorithms. So our neural network, we train that, we don't directly do that, but we actually do another simulation algorithm for the ChatGPT. What they do is a Monte Carlo tree search. But for our here, we will use every application to find out what is kind of algorithms we need to do. So this is actually another example can show you that inference time compute can help you to reduce the error of your machine learning predictions. So I don't have time. I just have 5 minutes. I want to show you the second kind of like a debiasing. So the second type of debiasing is also like iterative method, but for here we will use some kind of Newton method. So why we use Newton method here? It is because we know we can debias linear functional, but we don't know how to do nonlinear functionals. So to use linear functionals to approximate the nonlinear functionals, the way we know is to do Taylor expansion, right? So this is our second idea. So if you want to do the debiasing, you don't know what is exactly the bias, but we can compute out actually what is your Taylor expansion here. So if you do that, you may not get the exact unbiased algorithms, but you can improve your magnitude to like to a square. So you can still like improve the convergence rate, although it is not unbiased simulation. So this is our second idea, to use Taylor expansion to do that. Because I just have 5 minutes, so I will go through like very quickly on what we have gained, but not goes into the details. So the first thing we gain is actually ICML 2024 paper. So here is the details I will not go through. So we use this kind of idea for uncertainty quantifications. So we do first order Taylor expansion to do the debiasing. So we use the inference function as a debiasing method, but not use it as a jackknife idea. So in this kind of seeing, you will see that inference functions, we use inference function not as jackknife, but use as like a variance reduction. We can show you that you can use the same computational cost as jackknife, but get the same kind of result, the same kind of like guarantees as bootstrap. We know bootstrap is expensive, but computational expensive. So now we use the inference function as the variance reductor, so that we can use that to do approximate bootstrap, but it is like the same accuracy as bootstrap, but most of the computational cost is happens just computing out like the inference functions. So this is what we have made in 2024 SCaSML paper. So you can see many of the ideas can be used in different applications. But for today, I will show you that this is actually a Newton method. So why this is a Newton method? So the example I will show you is actually the simplest example, like to solve A inverse B or compute out the eigenvalue function, which is like the A inverse B method to build a linear solver using like the same thing I said, use like matrix and vector multiplication. I want to build a linear solver. So if you just use like estimated solution of my A, which to directly get your estimation, like this is what I have introduced before called randomized SVD, which is also have a name called randomized numerical linear algebra or sketching method. So it is that we directly estimate my A and plug in that as my solver to get my solution. So this is actually kind of thing is called sketch and solve, which means that, okay, we first using machine learning, which is called sketching to get an estimation, and we directly use that as a solver to get the approximate solution of like the linear solver or eigenvalue or eigenvalue computations. So now we will use our method here, like debiasing using Taylor expansion. A surprising relationship, we find out that our debiasing method is actually an inexact Newton method. So what we do is every step we will do like to get like a Newton step or to get a debiasing using the Taylor expansion. So now my phi here is actually A inverse B or eigenvalue of my A. So the phi operator here we give is actually a solution of a fixed point equation. So if now the functional phi here is actually a solution of a fixed point equation, you can find out that the debiasing term we're doing here is actually a Newton step. So this makes something like very surprising. So we just try to plug in like our result with like a inexact Newton method. So this is kind of like an algorithm we get. I will show it later. So, but I will tell you why this is an exciting result. When you plug in our result with like an inexact Newton method, you will find out that the previous stochastic approximation algorithm for linear solvers, they will always put like the stochastic approximation error like to the error every iterations. So you can see if you have an error bound looks like this, finally your error bound will become this thing times an exponential. But if you use that as like a inexact Newton method, you will find out that the error from the Newton is actually a higher order term. And the stochastic approximation error will happen as a contraction coefficient. So this means that if you use a stochastic inexact Newton method to debias that, if you have a better and better stochastic approximation, then the contraction number will become better and better, which means it will converge faster and faster if you have like a better and better like approximation. And we use that to design like eigenvalue solvers, which can be written down very, very simple, which looks like just an inverse power method. And here is just a stochastic approximation to the inverse. And if you do that, you can actually get a arrow bound looks like this, which is never seen before because previously this thing just appears as an arrow, but here these things will appears over like the contraction number, which will provide you like better and better convergence rate, which is just borrows the idea from the inexact subspace Newton method. And the second thing we can borrow for the Newton method is stochastic Newton type of method is actually not numerically stable. So once you have some like numerical float approximation, although the function value converges, the actual KKT condition will not converge. This is just be discovered last year. So last year we've people find out that if you do like stochastic inexact type of Newton method, this is actually not numerical stable. But if you go back to our iterative debiasing framework, it is just debiasing. So it is very, very easy to do numerical stable, like numerical stable solvers. So we based on this idea, we find out that if you the Newton type of method to do linear solvers is actually not numerical stable in float computations. But if you use the Taylor expansion debiasing framework idea, it can be easy for stability analysis. And based on that, we built the first numerical stable randomized linear solver, which is in this paper we just post on arXiv 1 week, 1 month ago. So the student working on this project is actually amazing, and who is finding PhD position next year. So if you are interested, you can see so there next year means the next cycle, but not this cycle. So if you are interested, you can look at his profile. Okay, so this is what I have talked about today. So today I want to show you a framework, which is we train a machine learning predictor, and we evaluate the error of the machine learning predictor, and then we use the simulation algorithm to debias the machine learning output. So which needs new analysis and new efforts to design algorithms. So the examples I have shown you, including compute the mean and the moments, trace estimation, high-dimensional PDE solving, large-scale like linear solvers, and uncertainty quantifications. So I'm also open to more applications in like operation management or others. So if you have like using your applications can be included in this kind of framework, I'm very happy to talk with you. So I think this is all for today, and I can take questions now.
Thank you, Yiping. Do we have questions? Shane, you turned on your camera immediately. Do you have a question?
I do. So thank you. That's really cool that you can take these couple of steps and accelerate the methods. I have a question actually about the simplest example that you presented, where you were just trying to estimate the average value of the function f. So I guess no need to go to the slides, but let me just ask the question. So you do two things, right? So the first is that you sort of use part of your data to estimate the function, and that gives you f hat. And then you use a different part of the data to estimate the difference between f and f hat. And then you combine those two elements. And you mentioned that you could use half the data for the first task and half for the second. And I'm guessing sort of in two parts. So first of all, the 50-50 breakdown is probably not perfect. And maybe there's good ways of figuring out what the right breakdown between the two is. And then assuming you've done that, is it also the case that there might be some analytical or clever way to symbolically essentially do that breakdown over all possible 50-50 splits, and therefore improve the, maybe not the rate of convergence, but maybe the constant?
Yes, yes, exactly. This is I think you already predict the answer. The answer is it will not improve the rate of convergence. But it will definitely improve the constant. So maybe you need to use like CLT type of result to compute out what is the exact variance and to see what is the best way to do the split. And maybe the second interesting question is actually I see there is actually literatures in the doubly robust estimators, they do not need to do the split. So we need to do the split because we need RID assumptions to bring out like our proof, right? So this is also another thing I think is possible, but can be hard. Is it possible to not do the split in the causal inference literature? They have paper to do that, but I still doesn't know what is the actual structure. I can go through the proof, but I still trying to dig out what is the structure there. So I think this can be another interesting thing to think about is we just don't do that. Can we do the things? And the third thing is, another thing I don't go through is actually our rate is the same rate as cosine Monte Carlo. So if you cleverly design your point, but not randomly point. So if you have randomly point, you need to do my procedure, but you have the point to do experiment design. Then it is the cosine Monte Carlo rate. The cosine Monte Carlo rate is the same as my rate. So it is not like one is better than other. So if you can do that, you can also do like experiment design. You can also do not need to do like these painful splits.
Okay, yeah, thank you. I guess sort of a related question, rather than saying, well, I guess what I'm curious about is it worth going to that extra trouble, or does a sort of a simple approach of just 50-50 data split, does that already get a pretty good constant?
I think it was to go it was to go that direction, but you just need to be careful. I don't know. So because you write down like the closed form things, right? The closed form asymptotics, but you actually don't know what is your function f. So this can be like some intuition to tell you how to split that. Maybe the function is hard, then you need to do something like that. It is good to see what is the quantity that controls these things, but I think it still can be very hard to like actually implement that quantity into like algorithms.
Gotcha. Yeah, thank you. Yep. Thanks very much.
Thank you.
Do we have other questions? All right, then since we're already a bit over time, let's thank Yiping once more. And thank you everybody for coming. And as a reminder, our next talk will be in 2 weeks when Céline Comté will be presenting on routing optimization for asynchronous federated learning on heterogeneous resources. See you all then.
See you.